Copolymerization is a type of polymerization reaction in which more than one kind of monomers polymerize to form a copolymer. Copolymers can be obtained by either chain growth polymerization or step growth polymerization. You already know that in contrast to copolymers, homopolymers are obtained by the polymerization of a single monomeric species. Here is a problem for you to try based on this concept. Identify the structures here as either a homopolymer or a copolymer. Structure A is a butadiene-styrene copolymer, BUNA-S. The monomers used are 1,3-butadiene and styrene. Structure B is a homopolymer, polystyrene. It is made from styrene monomers. Let us now understand how the properties of a copolymer differ from that of a homopolymer with a suitable example. BUNA-S, a butadiene-styrene copolymer, is elastomeric and tough, as in this bicycle tire. In contrast, polystyrene, a homopolymer, is brittle. As a mixture of two or more different monomers undergoes copolymerization, the copolymers produced have better physical and mechanical properties than homopolymers. For instance, the copolymerization of styrene with butadiene adds toughness, and with acrylonitrile enhances resistance to impact. The butadiene-styrene copolymer finds use in the manufacture of automobile tires, floor tiles, footwear components, and cable insulation. Let us now study rubber and elastomer in detail. Natural rubber is a polymer with elastomeric properties. It is obtained from the bark of the rubber tree in the form of latex. Rubber latex is a colloidal dispersion of rubber in water. Isoprene 2-methyl-1,3-butadiene polymerizes to form cis-1,4-polyisoprene, which is natural rubber. Thus, natural rubber is a linear polymer of 2-methyl-1,3-butadiene. The chains are held together by weak van der Waals interactions, and hence it is elastic and non-crystalline. The polymer chains form a coiled structure. Natural rubber can be stretched. When stretched, the chains get aligned in the direction of the external force. When the external force is released, the chains snap back to their original positions. Untreated natural rubber is quite sticky. It becomes soft at high temperatures, greater than 335 Kelvin, and brittle at low temperatures, less than 283 Kelvin. Natural rubber absorbs water. It is soluble in non-polar solvents and is susceptible to attack by oxidizing agents. These properties of natural rubber limit its usefulness. Hence, to improve the physical properties of natural rubber, a process called vulcanization is employed. Most rubber used today is vulcanized rubber. To vulcanize rubber, raw rubber is mixed with sulfur and heated between 373 and 415 degrees Kelvin. This forms sulfur cross-links at the reactive sites of double bonds, such as allylic positions, and thus the rubber gets stiffer. Commercially, Other substances called accelerators and activators are added to enhance the quality of the rubber. Let's look at the possible structures of vulcanized rubber. Notice the sulfur crosslinks between the chains. The vulcanization process is generally irreversible. The crosslinks help vulcanized rubber to maintain its shape when stretched. Vulcanized rubber is not very sticky, unlike natural rubber. Vulcanized rubber has high tensile strength and is usable over a wide temperature range. It is also resistant to abrasion. Vulcanized rubber has many uses. Perhaps its best known uses are car tires and shoe soles. Synthetic rubbers have also been developed. These are more flexible, tougher and durable than natural rubber. Synthetic rubber can be defined as any rubber-like polymer that can be vulcanized. Synthetic rubber must be elastomeric. It can be stretched and then must return to its original shape. Neoprene is an example of a synthetic rubber. This homopolymer is made from a monomer that is a 1,3-butadiene derivative, chloroprene. Chloroprene undergoes free radical addition polymerization to form neoprene. Neoprene is resistant to vegetable and mineral oils. It is used to manufacture conveyor belts, gaskets, and hoses. It has a wide variety of household and recreational uses as well. Another important synthetic rubber is Buna N, also known as nitrile rubber. It is a copolymer of 1,3-butadiene and another unsaturated monomer, acrylonitrile. A peroxide catalyst is required for the reaction. The overall equation is shown here. Buna N, or nitrile, is resistant to petrol, lubricating oil, and organic solvents. It can be used over a wide temperature range, and so it has many applications in automobiles. Buna N is used to make oil seals and tank linings. Non-latex disposable gloves are typically made from nitrile. The molecular mass of polymers determines most of their physical properties, such as viscosity, tensile strength, and toughness. The better the physical properties of a polymer, the more is its commercial importance. That is why the study of the molecular mass of polymers is important. You already know that polymer molecules have extremely large molar masses. However, polymer samples are a mixture of molecules with different numbers of repeating units. The different sized chains of molecules present in the mixture of a polymer will account for its overall behavior. In other words, the behavior of a polymer depends upon the availability of monomers in the reaction mixture or the way the polymer is produced. Therefore, the molecular masses of polymers are best described as a distribution of molecular masses. So, when we discuss molecular masses of polymers, it's most appropriate to discuss average molecular masses. We can calculate the average molecular mass in two ways: number average molecular mass and weight average molecular mass. Number average molecular mass Mn is essentially an arithmetic mean. To calculate number average molecular mass, find the total mass of polymer molecules and divide it by the total number of polymer molecules. Weight average molecular mass is indicated by MW. The formula to calculate MW is given here. The molecular mass of polymers may be determined by a variety of methods. These include dilute solution viscometry, size exclusion chromatography, mass spectrometry, light scattering, and ultracentrifugation. Let us now study biodegradable polymers in detail. Let us first try to understand how most synthetic polymers cause environmental hazards. Most synthetic polymers are non-biodegradable and persist in the environment for a very long time. These polymers are responsible for the accumulation of solid waste, which causes acute environmental problems. Let us see how polymers, such as plastics, pose a serious threat to the environment and, of course, to human life. Although plastics have become indispensable in our lives, they cause many environmental problems. One major problem is the accumulation of plastic waste or toxic substances. For example, the clogging of drains by polythene bags and other plastic material causes floods in cities. Animals mistake plastic for food and choke on them. Plastic may also get entangled in the intestine and cause an agonizing death. Plastics do not degrade for a very long time. Discarded plastics fill up landfills, which, in due course, results in the contamination of soil and water. The Great Pacific Garbage Patch consists mostly of plastic bags, bottle caps, and styrofoam that have been swept away into the ocean from poorly secured landfills and other sources. It is a serious threat to marine life. You can choose better alternatives that will help reduce the use of plastics. Use soluble starch pellets instead of styrofoam packing. Use reusable cups instead of disposable plastic cups. Bring reusable bags when shopping and make sure polythene bags stay out of drains. Recycle your plastics or reuse them instead of just throwing them into the trash. Many plastics can be recycled. Recycling starts with the collection of post-consumer and post-industrial plastics. Once the plastics have been collected, they need to be sorted. In principle, many polymers can be recycled. In practice, the most commonly recycled plastics are thermoplastics such as PET, polyethylene terephthalate, and high-density polythene. Plastics are recycled by type and then by color. Finally, the samples are subjected to chipping, which involves chemical treatment. After chipping, the plastic can be reused. Can you list 3 steps that you could take to improve plastics recycling in your neighborhood, community, or school? There are many ways that you can do this. Here are some suggestions. You could organize recycling collection stations in your community or at school. encourage local merchants to participate. They could sell reusable bags and collect plastic bags for recycling. One company in Bangalore uses discarded plastics to make roads. Keeping in view the potential environmental hazards of synthetic polymeric waste, certain biodegradable synthetic polymers have been developed. Biodegradable polymers that are synthesized contain functional groups similar to the functional groups in biopolymers, such as wool, silk, and cellulose. The copolymerization of 3-hydroxybutanoic acid and 3-hydroxypentanoic acid forms a synthetic biodegradable polymer PHBV, polybeta hydroxybutyrate co-beta hydroxyvalerate. Notice the ester linkage in the repeating unit of PHBV. PHBV is used for specialty packaging. Because it is biodegradable, PHBV is used for medical sutures that don't have to be removed after surgery, and for controlled drug release. Here is a problem for you to try. Nylon 2 Nylon 6 is an alternating copolymer of glycine and aminocaproic acid. Can you write the equation showing its formation? Glycine and aminocaproic acid form an amide linkage by condensation as shown here. Notice how the polymer has a 2-carbon group and then a 6-carbon group in the repeating unit. Nylon 2 Nylon 6 is a biodegradable polymer. Another biodegradable polymer is polycaprolactone or PCl. PCl is used for medical sutures, drug delivery, and the manufacture of specialty polyurethanes. It has even more applications when blended with other polymers. PLA or polylactic acid is another biodegradable polymer. The starting material is plant-based, derived from cornstarch or sugarcane. Lactic acid is dimerized to make the lactite monomer, which undergoes a ring-opening polymerization. PLA is being used for packaging, such as cups and take-out containers for food. However, it can only be used for cold beverages and cannot be used on very hot. It has various consumer uses, such as fiber for clothing and medical applications, such as sutures and stents. Commercial composting facilities are needed to break down PLA, and it is more expensive than PET. Using biodegradable polymers has some benefits. They don't require incineration, so they lower carbon dioxide emissions. They decrease environmental pollution as they can be readily degraded. They can be used as internal sutures that don't have to be surgically removed. Commercially important polymers include polycarbonates, polyvinyl chloride, glyptyl, polypropylene, polystyrene, urea formaldehyde polymers, bakelite, and polyurethanes. Let's look at each of these in turn. Polycarbonates are a group of polymers named for the carbonate groups holding the repeating units together in their backbone chain. These are thermoplastic polymers that belong to the class polyesters. The most common polycarbonate is made from bisphenol A or BPA, a diphenol, and carbonic acid. The formula for the polycarbonate of bisphenol A is shown here. Polycarbonates have high impact resistance. They are transparent, but they can scratch easily if not coated. Therefore, they are useful for spectacle lenses, compact discs, bottles, and shatterproof windows. Polyvinyl chloride, or PVC, is obtained from the free radical polymerization of vinyl chloride, as shown here. PVC is resistant to water and fire. It is used to make shower curtains, raincoats, pipes for plumbing, vinyl siding for houses, flooring and electrical insulation. Glyptyl or alkyd is a condensation polymer formed from phthalic acid and glycerol, or phthalic acid and ethylene glycol. Glyptyl is a polyester that can form cross-links. Cross-linked glyptyl is a thermosetting polymer. Glyptyl is used in the manufacture of paints, lacquers, and resins. Polypropene is an addition polymer of propene. It is abbreviated as PP. Polypropene has a range of uses. It is used in the manufacture of medical equipment, laboratory equipment, electronic equipment, and automotive components. It is also used to make ropes, toys, pipes, fibers, and so on. Polystyrene is a homopolymer of styrene. It is commonly referred to as styrofoam. It is used in the manufacture of toys, radio and television cabinets, plastic cups, packaging, and food containers. It is also used as an insulator. Urea formaldehyde polymers are formed from the condensation reaction between urea and formaldehyde. Urea formaldehyde polymers are used for making unbreakable cups and laminated sheets. Bakelite, a phenol formaldehyde polymer, is another commercially important condensation polymer. Bakelite is used to make combs, phonograph records, electrical switches, utensil handles, and computer disks. Bakelite is also used as a porcelain substitute, such as in game pieces. Polyurethanes are a class of polymers with a urethane linkage. The formula for a simple polyurethane is shown here. In general, they are made from two monomers, a diisocyanate and a dihydroxyalcohol. Can you draw the chemical structures of the two monomers used to synthesize the polyurethane shown here? Remember that polyurethanes are typically made from a diisocyanate and a dihydroxyalcohol. Working backwards from the polymer structure, we can draw these two structures. Polyurethanes are very versatile polymers. Their many forms include foams, elastomers, and fibers.